Good morning, everybody. Welcome to the third day of our INSPYRE school. This year we are only online due to the sanitary situation, but we are really eager to say that the participation is not so small. So thank you everybody who are connected. And let me introduce the subject of the today's session that is entirely devoted to nanotechnology. And the first speaker of today is Dr. Stefano Bellucci. Stefano is a senior researcher of the National Institute of Nuclear Physics. He started his career as a theoretical physicist, and more recently he moved to this subject of nanomaterials, and he became a real expert in this field. So you will have the chance to learn a lot about nanomaterials, and above all about nanomaterials used for biomedicine. So please, Stefano, take the floor and tell us all the beauty of this subject.
Okay, thank you very much for the introduction. Good morning, everybody. So today I'm going to talk about nanomaterials for biological and medical applications. Okay, I have written here that I'm leading this next group, which I founded in the year 2000, so about 20 years ago. That's when I made the transition to nanotechnology in my career. So now, where should we have been is given in this slide. This is the largest national laboratory of the National Institute of Nuclear Physics in Italy. And okay, here is where I normally work. Now, my group has been working, as I said, for 2 decades. That explains why the wide variety of subjects that we've been considering with nanoscience and nanotechnological application of this science. So here you see on the top, you see the synthesis of different nanomaterials. As you move to the left anti-clockwise, you see that we are equipped to observe by microscopic characterizations as well as spectroscopic characterizations in-house in my lab, our nanoparticles. Then we have a strong vocation for theory, modeling, and also the computer simulation of our structures and their physical and chemical properties. And the applications range from sensors. Today I will speak particularly of bio sensors, but there are sensors also to gases or to other types of analytes, not necessarily of biological interest, that we are normally working on. And true genuine medical applications that have to do, on the one hand, with toxicology. That is explained from the caution in approaching these new materials that can pose threats to the health of the professionally exposed workers, to my students, to myself and others. And so we have to keep this under control by examining the biocompatibility of the materials we produce. Once we test this biocompatibility, we are going to use the nanoparticles also for controlled and targeted delivery of drugs of interest. There are also electronic applications that we've been working on for many years, financed also by the European Union very widely, very largely, and that have to do with interconnects. Nanocomposite materials, that's a special type of materials that include nanoparticles and have applications in, for instance, in space science or in aeronautics, or even in commercial products. And so I now give you, first of all, an introduction to what is a nanoparticle and how it can be used, and how, in fact, it is already in use in our society since many, many years. You will be surprised how much nanotechnology has already penetrated in our everyday life. And here you see the wide range of applications of nanoparticles. Nanoparticles are put at the center of this type of structure, concentrical circles. In the next circle, I have put different areas of application, from textile to biomedical to genuine healthcare to applications in agriculture and food, not only production but also packaging, true genuine industrial, hard industrial application, from the production of industrial additives to pigments for paints, for instance. Needless to say that the most successful commercial application of nanoparticles has been historically developed in the 90s by an American and a US multinational company that developed paint based on titanium, nanoparticles of titanium dioxide. Electronics applications I've already mentioned, and they are now present practically in all electronics equipments. Environmental application for detecting pollution and also introducing suitable filters for water pollution remediation and more recently air pollution remediation. I must say that the soil treatment is probably what needs to be more developed at this point, but it is a little bit lagging behind in research worldwide. And finally, renewable sources of energy. Let me give a first definition of what is nanotechnology. I've written here, it is the science of manipulating matter at the atomic and molecular level with the aim to achieve materials and devices, I should add, which have specifically enhanced properties from the chemical and the physical point of view. I've written here essentially 4 areas. I've reported 4 areas that are the areas where the major innovations are, on the one hand, necessary, on the other hand, potentially provided by the help of nanoparticles use. So IT, where we need to have smaller, faster, and especially energy efficient IT systems, information technology systems. To medicine, we will deal with this practically throughout the course of this talk. We will discuss treatment of cancer diseases, how to apply nanoparticles to the treatment of bone problems, drug delivery, and so on. Diagnostics is a particularly important topic, and we will see there are applications I will not discuss for lack of time, like the improvement of imaging, for instance, echography, by using nano devices and nanoparticles. Then energy. Energy, of course, is one of the most wanted application in our society. We have a greed and a hunger for production of energy to replace the conventional fossil fuels with renewable sources of energy. And nanoparticles potentially can help solar cells as well as batteries a lot. In my group, we are working currently on batteries using carbon nanomaterials. And finally, consumer goods already include nanoparticles, from the foods and beverages, where the nanoparticles are already used to obtain advanced packaging materials, to put sensors on our miniaturized sensors on our packaging, so that we can, for instance, ascertain whether a frozen good, has been preserved in a proper way, or has it been out of the fridge, out of the freezer for some time. We can put a sensor that will label and register the history of the product. Other applications that are interesting, we'll discuss them, have to do with smart textiles that can be stain-proof, waterproof, and wrinkle-proof and wrinkle-free. Household and cosmetics are already including, for instance, in sunscreens, nanoparticles. What are the basics of nanotechnology? Why nanotechnology is working so well? First of all, as I said, you work at a very, very small level, very near the atomic level, and the scale of the lengths ranges between 1 and 100 nanometers. We're going to see immediately in more concrete terms what does that mean. But let me stress that the aim of the nanotechnology application is not only to achieve very small devices, very small meaning what I said in the previous point, scale of length between 1 and 100 nanometers, but to achieve the realization of a device where having such a small structure, at least in one of the three space dimensions, yields fundamentally innovative properties. So nanotechnology means that because we have a thin film or a small particle, then we have a new property, a new property that we can use to our advantage. What is the reason? I promise to explain. It's very simple. It's a very large surface to volume ratio. That means that we have an extremely large surface area in a nanoparticle. For fixing ideas, imagine that a particle, let's say not nano, but more like microparticle of 300 nanometers diameter has a, well, substantial but not extremely high number of atoms placed on its surface. That means 5% of its atoms are placed on the surface. If you only scale down by factor 10 from 300 nanometers down to a smaller diameter of 30 nanometers, thus entering truly the range of nanotechnology, then the percentage of the surface atoms is tenfold, is multiplied by factor 10, and becomes half of the total number of atoms. That explains why nanoparticles have such incredible properties that I will try to illustrate in the next part of my talk. And here is a classic example taken from the internet, where you start from a cube of gold with 1 meter side. The total surface is easily calculated, is 6 square meters, and can be covering for instance, the floor of a very small room, 8 feet by 8 feet, because it's taken from the US site. Now, if you break the side of the cube into 4 parts, then you multiply the surface by a factor 4. You scale up from 6 to 24 square meters. If you imagine repeating this operation until you get to a very tiny size, that is 1 nanometer, then the mass remains the same, but the total surface is enhanced to about 4,000 square kilometers or 2.5 thousand square miles. That would cover the surface of a medium-sized state in the United States, or in Italy, a medium-sized region. So I promise to explain what is a nanometer. It's readily said, it's a millionth part of a millimeter, or if you want, is a 1,000 times smaller than a micron. Imagine a micron is about 1/50th of the thickness of a human hair. 1 nanometer is as big as a layer of few atoms, 3 to 5, because remember, an atom has a scale that is typically on the angstrom. An angstrom is the 10th part of a nanometer. Here you see a scale that ranges from the atom on the angstrom scale, 10 times larger, you get to small dye molecules, about 1 nanometer, and then you go higher and higher and meet different systems, physical or biological systems like proteins. And then you get to a bacterium. A bacterium is about 1 micron, and animal cells are about 10 micron. A virus, because nowadays we talk a lot about viruses, are typically a few hundred nanometers, so about between the colloidal gold particles and the bacterium. So if we want to compare this size to the human size, you can start with a tall man, about 2 meters tall, reduce by factor 1,000 its size, get down to the size of an insect, like a mosquito, is about 2 millimeters, reduce by factor 1,000, and we get to a feature of the mosquito, like its eye, is about 2 micron size. If you get down by additional factor 1,000, you get now finally to the basis of life. That is the DNA. The DNA typical molecule size is 2 nanometers. So all in all, we have proceeded to divide by a factor 1 billion the size of a human being to get down to the basis of living organisms, that is the DNA, and it is a truly nanometric object. Now, in nanotechnology, we have available two routes, two ways of realizing nanoparticles, a top-down and a bottom-up strategy. In the top-down, you simply break a macroscopic object in very tiny fragments until you get down to the size of the nanometer, let's say 100 nanometers or less. See here an image which is made in silicon. It has been excavated by a beam, and this beam produces tiny features in the London Bridge. So these tiny features are nanometric. And on the right-hand side, you see a bottom-up approach example. You can imagine, you can figure it out as a kind of a Lego system assembly. Here, nanofibers, in this case, are carbon nanofibers. They've been self-assembled to realize a knot, so a topologically non-trivial configuration. In my group, we've been pursuing mostly the bottom-up approach, on the one hand, because the top-down requires instrumentation that is very costly, like transmission electron microscopes, like nano beams, and so on. On the other hand, it is also, in my opinion, the approach that is more easily scalable to the industrial application. So with an eye to not only carrying out basic research, but also trying to develop concrete applications for society, we favor this bottom-up approach. And here you see two books that we've been publishing in the past to put together the experiences that have been done by my group and collaborators in these areas. Now, nanotechnology is not entirely new in the sense that unintentionally, ancient people were already practicing nanotechnology. Here you see an artist named Lycurgus, who was also a good material scientist, in the 4th century of the current era, produced this cup, which is nowadays preserved at the British Museum in the UK. This has an interesting feature that is, if you use light in reflection, that means you put a source of light outside of the cup, then the cup looks green. If you put the source of light inside, then the cup looks red. That is due to the presence of nanoparticles of noble metals, in particular gold and silver, inside the glass paste. So here you see a TEM, transmission electron microscope image of the nanoparticles that are present in the Lycurgus cup. Also in the Middle Age, things went on with using nanoparticles. Metal nanoparticles of different types of elements were put in the stained glass windows of medieval churches. On the right top, you see an image of the transmission electron microscope of the nanoparticles that are present in the composite, in the glass composite. You see that they are very small. We talk about 10 or 15 nanometers diameter, and you see also that they are structured inside, so they have a crystalline structure, and I don't want to get into too many details. Just let me convey the message that this type of technology is obviously of the top-down kind. You see here the pestle and mortar that these people were using to obtain nanoparticles with a grinding process that lasted a long time. So that's a top-down example. How do we see this type of arrangements at the atomic level? There have been in the past, there have been in the past, in the recent past, in 1990s, there have been striking results obtained by the IBM group, which were able, this group was able to arrange 35 atoms of xenon on a nickel surface with a certain lattice structure, 110 in particular, of course at very, very low temperature, otherwise the atoms would vibrate and would move around a lot, will oscillate a lot. So they decided to put them in an order structure, for instance, in this case, IBM. It took about 22 hours to complete this image. That was an opposite type of approach. It was a bottom-up approach, as we will see in a minute. And it was achieved using an STM, a scanning tunneling microscope. powerful instrument at the time, totally new, developed by this group. On the bottom, you see near the kid who's observing with a standard optical microscope, which of course is not an electronic microscope, is not enough to observe nanoparticles. I put it here just for fun. You see another type of microscope that is an atomic force microscope, briefly AFM, which scans the surface of a film and identifies the roughness, the highs and lows on the surface by using a laser beam that hits a cantilever equipped with a tip. This tip is scanning in different modes, tapping, contact, non-contact, and it can give us the characteristic, the very tiny features of the surface up to the atomic layer with atomic level precision. Here you see how the film, the IBM was made. IBM was written starting from a disordered assembly of atoms and then progressively ordering them using an STM, about 22 hours. Another curiosity, in 2013, the smallest film in the world was realized. I challenge you to make a film that is smaller than that. It's entitled A Boy and Its Atom. It was made again at IBM. And you see a boy made of atoms. In this case, it's again silicon, I think silicon atoms on some substrate, but I'm not sure. And here an atom is coming and the boy is playing successfully. Now let's get into some more specific topic, that is the use of carbon in nanotechnology. Carbon is the basics for life, so no surprise that we're going to use such abundant and useful elements for realizing systems and devices at the nanoscale. Now, on the left bottom, you see the diamonds, which is a cubic lattice. It has special optical properties. I'm not going to spend time on it, like total refraction, that make it interesting from the commercial point of view. But you're more familiar with graphite. Graphite is given at the center of the diagram of the carbon family. It's another allotropic state of carbon, and it's interesting because it has a very strong bond on the XY direction, on the planar direction, whereas the different planes that make the graphite are only weakly bound one to the neighboring one. So it's easy to separate the layers of graphite, and in this sense, one can think of obtaining what is put on the top right corner of the picture, namely graphene. That would be a single layer with atomic thickness of the layers that make the graphite. However, it was the last one to be discovered, only in the 2000s, because with a very simple way, and we will discuss it later on, because before, in the 80s, fullerene was obtained, starting from graphite. The fullerene is not made purely of hexagonal lattice, like graphite or graphene, is made rather by a mixture of hexagons and pentagons. Without the pentagons, which are, you can think of them as a defective hexagon where one of the atomic links has been removed. These defective sites are necessary to obtain a curved structure. Otherwise, you will never close the structure to form a ball. This fullerene is also called buckyball. It's in honor of an US architect who used to create in the 1940s architectural structures, for instance, covering of swimming pools or gymnasiums or things like that in different American universities, using this structure, hexagons and pentagons, let's say half of a fullerene molecule. The smallest molecule, made obviously of carbon atoms, is made of 60 atoms, and that is why it's called C60, but there are C120 and bigger molecules. Let's move to the last picture on this slide, that is the carbon nanotube on the topmost left picture. You see here that is essentially a structure you can think of obtaining by starting with a graphene layer and rolling it up in cylindrical shape, namely defining an axis of symmetry and then rolling up the plane around this cylindrical axis to obtain a single layer carbon nanotube. What is a carbon nanotube? Let's start from that, because historically, in the end of the 90s, I started working with carbon nanotubes, first at the theoretical level, then in 2000, setting up my laboratory to produce them and use them. They were discovered, at the time they were quite new, they were discovered in the early 90s by Sumio Ijima in Tsukuba in Japan. They're hollow cylinders, long and thin. You can think of them, as I said, as a sheet of graphite or graphene rolled up into a cylinder, and you can have it open or closed. If you close it, you have to use 2 half molecule of fullerene to close it. So they can be distinguished in a single wall, as we saw a minute ago, but also you can create multi-wall nanotubes that are coaxial cylinders, one into the other, a little bit like Russian dolls. More or less, the features are similar in the sense that the long and thin single-wall nanotubes have a higher aspect ratio. The aspect ratio is simply the ratio of the length over the diameter of the object. So in this case, we're talking about, I don't know, typically 10 to the 3, 10 to the 4 micron divided by 1 or 2 nanometers. So we're talking about 10 to the 6, 10 to the 7 aspect ratio. So it's very, very high, 1 million or 10 million value for the aspect ratio. For the multi-wall is a little bit smaller because the multi-wall are thicker. They range between 5 and 200 nanometers, and the length can reach up to, even nowadays, even a millimeter or a fraction or a millimeter. What's so special in a carbon nanotube? A carbon nanotube has a very high aspect ratio. That means it's a quasi-unidimensional structure. It has a very terrific mechanical properties. In terms of elasticity, its Young modulus, or elastic modulus, is about 1 terapascal, which means orders of magnitude higher than special steels, for instance. It has the ability to carry very high density of current. That means that can replace copper, which we normally use for the transport of current. This can reach up to 10 to the 9 ampere per square centimeter. And finally, it has very, very high thermal conductivity. That means that its thermal properties are suitable, for instance, for space applications in re-entry vehicles that need to realize shields that can sustain the very high temperatures in the re-entry in the atmosphere. How do we realize these carbon nanotubes? Arc discharge, laser ablation, chemical vapor deposition. So we have in our lab arc discharge and chemical vapor deposition. The arc discharge is a physical method based on voltaic arc. The chemical vapor deposition is a chemical method, obviously, that is based on a precursor that is a gas. It's a carbonaceous gas that is normally decomposed at high temperature, ranging from 600 up to 1000 Celsius, more or less, depending on the type of material you want to obtain. And the decomposition of the gas, for instance, methane, CH4, you decompose it and the carbon atoms become available to rearrange in a desired structure, for instance, a carbon nanotube or graphene. All this can be engineered. Now, there are advantages and disadvantages, but basically, the arc discharge can yield very pure material, which doesn't need any purification using strong acids or other chemical methods, whereas chemical vapor deposition yields, on the other hand, the possibility of realizing large quantities of material, which is more difficult using arc discharge. Here you see historically our first chamber that was assembled in my lab in 2001 for realizing carbon nanotubes. And you see the electrodes are between the electrodes that are made in pure graphite. A voltaic arc is struck, the temperature very high, thousands of Celsius, very near the axis of the arc. And then you see the nanotubes have magnifications that are increasing by SEM, by scanning electron microscope, up to the level of seeing the individual multi-wall nanotube with 19 nanometers diameter. In this case, is a 150,000 times magnified image. Very nice one. You can see how straight the nanotubes are. That means that they have very high mechanical properties. Well, I give you here immediately an application that is as old as 2007, the Ferrari F2007, that actually with Raikkonen won the Formula One championship that year, was a concentrate of nanotech, from brakes that contain carbon nanotubes to the car body made of ultralight material that is a composite where carbon nanotubes are in a small percentage inserted as a filler, and finally special tire compound that uses carbon nanotubes inside the elastomer that makes the matrix of the composite. Now here, what properties are we using? Well, in the brakes and in the compound, we are using the thermal properties, because these thermal properties are responsible for the high performance of brakes that need to dissipate heat very, very fast, and the same happens during the brake phase, the braking phase, and the compound, the same. In the compound, you have adhesion to the asphalt is given essentially by the high capability of the compound to dissipate energy and transmit it, homogenizing the temperature on the tire to avoid breakdown of the tire. The car body, here the use of the carbon nanotubes is essentially because they give very high mechanical properties without putting too much weight in the car, because they are hollow, so they are very, very light. Here you see an example of the Symbionts car that was presented a few years ago at the car show, I think in Paris or in Geneva, I don't remember. That is a collaboration of a US college in California and a German institute, also where students were involved. Essentially, the Symbionts vehicle runs on solar piezoelectric energy, because carbon nanotubes, apart from solar cells that the car is equipped with and the standard CARES for recuperation of the energy in the braking, but here there are carbon nanotubes on the body of the car because they exploit friction with the air during motion to generate electrostatic currents, that's electrostatic charges, that then recharge the battery of the vehicle. On the right-hand side, you see a flexible mobile presented by Samsung a few years ago. Here, the technology is OLED. OLED is organic light emitting diode, which means that we have an active matrix light emitting diode embodied into the screen. So the pixels are creating their own light source. You don't need a backlight like the standard liquid crystal display screen technology. You have a circuitry that is fused into a very, very tiny layer of glass. That explains the performance and at the same time the flexibility. Nanotechnology is also normally in use in cultural heritage. And here is an example of a fresco in Florence, where calcium hydroxide nanodispersions have been used for nano cleaning. So you see on the right-hand side the images at the transmission electron microscope of 2 nano-sized particles that are used in the dispersion or in the suspension. And they have different shapes, different structures. The A is a hexagonal calcium hydroxide. The other one is a carbonate, and it's prismatic. In all these devices, often we use nature as a guidance. So we imitate nature. That is why we have biomimetic devices. You see an example on the left where you see the water droplet on a cotton layer, which has been coated by titania nanoparticles, which have a diameter of 100 nanometers or smaller. And this coating allows essentially the realization of an artificial imitation of the lotus. The Lotus Leaf displays what the property called Lotus effect, where the droplet of water cannot be absorbed and remains on the surface of the leaf. And so it happens in this cotton layer. On the right-hand side, you see examples of nano cleaning. You have a comparison of treated, coated with nanoparticles and standard uncoated devices that go from concrete walls to a handle, for instance, in emergency exit, to tools for work. And in energy, I could speak an hour or two on energy, so I'm not going to give you all the details of batteries or solar cells and how nanoparticles are being used in those devices, but I only give you a curiosity, that is the nanofelt or power felt. This power felt is a felt, and it has been surrounded by essentially by an architecture, an electronic architecture that aims at exploiting the difference of temperature between the body of the athlete and the cool air outside. So if we have, this has been developed at Wake Forest University Center for Nanotechnology and Molecular Materials in the US, and it's based on thermoelectric power generation. So what can happen here, thanks to the presence of carbon nanotubes in the power felt, is that in the presence of a gradient of temperature of only 17 Celsius, so if the air is about 20 Celsius and the body of the athlete is 37, then you have a production of 100 millivolt per square meter of felt. This can be enhanced by, of course, increasing the number of layers of felt or increasing the size of the nanotubes that have been used to realize the felt. Another example is in cosmetics, and as I mentioned before, nanoparticles have been inserted into the sunscreen to enhance the UV protection through the dispersion of nanoparticles inside. Here you see the image of nanoparticles. They show you that the nanoparticles are about 4 or 5 nanometers in diameter, and their structure, their atomic, their lattice structure has an interlayer distance of a little bit more than 2 angstroms. So I hope I convinced you that nanotechnology has many uses. In this sense, it's very pervasive because it can penetrate in different technological areas. It's also enabling technology, like, for instance, an example of enabling technology is electricity. Electricity was discovered in the 19th century, essentially, or developed, let's say. It was discovered in the century before, but it was developed in the 19th century by Michael Faraday and James Clerk Maxwell for only one application, essentially, illumination of big cities like London. Those are the days of Jack the Ripper. So you need to illuminate much better than with the gas. They were using at the time acetylene, which has a very low performance. But then, once it was discovered, already at the beginning of the 20th century, the uses multiplicated, and mankind got to the level, to a technological level that was completely inconceivable only a few decades before, and led to the discovery of computers, radars, smartphones, all of this based on the use of electromagnetism in a clever way. That is the concept of enabling technology, a technology that leads you to a completely different plane of technological development, enabling you to think and conceive something that was inconceivable before. It's also an ubiquitous technology because you find it pretty much everywhere, from solar energy to batteries to weapons to instrumentation, design, and manufacture. In all applicative areas of interest for mankind, nanotech can play a role now or in the medium-time future. That explains why in the next part of my talk, I will concentrate on, first of all, assessing how dangerous it can be. In other words, what can be its impact on environment and on human health, and in particular for people working with it. So now we stop and take up a few of your questions before moving on.
Thank you, Stefano, for this very nice overview. Yes, we have many questions, so I will try to pick some up. The first one is really interesting. So you said that these nanoparticles are really very small. So there is a worry that by breathing, this particle can enter our body and can then interact with the DNA. Can be this true, or can you say something about that?
I will devote the second part of my talk to answering this question.
Okay, well, then I pose you another question that said, can we apply nanotechnology for reproducing organ cells?
Okay, this I will not treat this subject because of lack of time. It's a very interesting subject. It's called the realization of scaffolds, and cultivation of cells can be achieved using nanostructure scaffolds as a substrate. So the answer is yes.
Okay, good. And another one is concerning this material, these different layers of felt, is asking if having more layers of felt, if the difference in temperature will change for every layer. Is this a problem?
No, the temperature will not change. I mean, essentially, the device is immersed in the same air. So essentially, what happens there is that the increasing of the number of layers will increase the voltage that is produced by the device with the same gradient of temperature. Another way, of course, is to increase the gradient of temperature, but that is trivial.
Unfeasible, yeah. And another question.
If you run in Alaska in the winter, it will happen.
Yes, but okay. Not interesting. Okay, another things regards they ask if you need a material with a certain property, how do you understand which shape you need to give to obtain this kind of property?
Mm-hmm. That's a very interesting question. It's one of the handles we have to engineer our nanoparticles. I will show you in the third part of my talk how to create not only a particle of a certain shape that has been engineered for a specific purpose, for instance, penetration inside the cell, but also how we can attach different functional groups to this nanoparticle to make it, for instance, suitable to target a special tissue or a special antibody or a special organ in the human body.
And I think we can conclude this question session with a question concerning IT technology. So at which level, for instance, Intel or other company develop their own computers using the nanotechnology available?
That's the most challenging topic in nanotechnology. In fact, already since decades, people have been trying to propose carbon-based circuitry to realize chips, but also more in general architectures, for instance, horizontal or vertical interconnects. The problem with the companies, the semiconducting companies, are very reluctant to leave the silicon technology and embrace the carbon-based technology for electronics. That is due to considerations that have to do with commercial strategy. On the one hand, carbon nanomaterials are still much more risky in terms of obtaining a number of devices that are functioning well. A lot of waste is generated, and the costs are still too high. So nowadays, a company realizing semiconductors chips, they can make millions and millions per day at very low cost, less than a cent each device. So if a fraction of this is defective, they simply throw them away. If you do the same with carbon nanomaterials, the costs are factors of 10 higher, and so you cannot throw them away so easily. And the number of failures, the percentage of failure is not small at all. So that explains why in our computers, you don't have yet a purely carbon-based technology. However, hybrid technologies marrying semiconductor materials based on copper and based on silicon with carbon nanostructures are already being developed, not only by Intel, but by other companies, ST, for instance, ST Microelectronics, that is a European company.
So essentially, it's matter of time to have more reliable process to realize this device.
In an optimistic view, I would say yes.
Okay. So please, Stefano, go ahead and tell us the rest of your talk, please.
Okay. Thank you. In the second part of my talk, I'm going to assess the impact of nanotechnology on health and the environment. So the road starts being steeper. And here you see, I present you two books that we realized in 2009 and 2010 for the Italian edition, and 2011 for the English edition. In the left-hand side, you see the application of nanoparticle and nano devices in biology. On the right-hand side, you see the exposure of occupational health workers and to engineered nanomaterials. Remember this word engineered, we will get into it, and safety effects. This was done in coordination with the Italian institute that devotes its activity to the protection of exposure of professionally exposed workers. In Italy, it's called INAIL. And I was the first signer of this white book. Then in 2015, the European Union took up our recommendations on best practices and delivered the directive that was essentially disciplining, norming all the devices that contain nanoparticles defined as objects with 100 nanometers or less in size. And here, by the way, I mentioned the problem of fullerene that dissolved in water can bind to DNA and therefore can change its structure and stability. So truly the question that was addressed before is a concern. So what are the grand challenges of nanotechnology in general? As you can guess from the fact that these materials are very, very interactive, they have a very high surface to volume ratio, so they interact with the environment a lot. They're difficult to keep them, it's difficult to keep them stable, and not only it's difficult to handle them. In addition, there is a fundamental difference when you deal with nanoparticles compared to when you deal with much bigger size particles. In other words, a single particle of, for instance, silicon, to pick up an element, does not behave at all like a bulk silicon and needs to be studied, and also needs to be studied not only in the lab, but also when you put in the environment where it's supposed to work, for instance, in a living system. Then there is important attention must be paid on the dependence of the properties on the not only the size and the shape, but also on the surroundings of the particle. In this sense, we developed in the past few years the notion of biocorona. Here you see the example. The nanoparticle is made at synthesis, characterized. We know all about its physical, chemical properties. Then, however, it crosses the biological barrier. For instance, being inhaled accidentally, or we inject it in a tumor to cure the tumor. So we do it intentionally. In both cases, the nanoparticle changes when it crosses the biological barrier, entering the living organism, and gets surrounded by a biocorona, this red thin layer that I put on around it. Then normally, this is a feature of almost universal feature of nanoparticles, independent of its shape, but it can be enhanced and fostered by engineering the surface of the nanoparticle as well as its shape. A phenomenon takes place when the nanoparticle gets close to a cell. Namely, the phenomenon is called endocytosis. Basically, the plasma membrane creates like a pocket, and finally a vacuola or a hole is created by lysosome where the nanoparticle is now placed. And it stays in the cytoplasm of the cell for a certain time before being kicked out. This phenomenon is called the exocytosis, where the nanoparticle leaves the cell cytoplasm. But notice that the color of the biocorona is changed. It's changed because proteins, enzymes are put by the cell around the nanoparticle. So we need to study all this. And in particular, you see here nanoparticles produced during the combustion process accidentally, and that can be studied both epidemiologically as well as toxicologically. We have nanoparticles that are used intentionally in industry, for instance, as industrial additives, and that gives a nanotechnological machinery. In all these cases, we are driven by the application because, of course, we aim at very high performance. But on the other hand, we need to have in mind toxicological prescriptions and industrial hygiene strategies, and that requires the introduction of norms and regulations that have been already studied and are currently studied in the highest political instances. Okay, here you see examples of our studies in 2008, for instance, on toxicity. We studied the proliferation of cells, how it is changed by the presence of multi-walled carbon nanotubes using human arterial smooth muscle cells, HSMCs. Now, applications can also, for instance, in this work that we published in Sensors and Microsystems in 2011, can also have to do with the use of films of carbon nanotubes to cure skin cancer, for instance, by applications of patches. And here, the toxicity is working to our advantage, especially the type of toxicity that is called apoptosis, or programmed death of the cells. So we are entering now the kingdom of nanomedicine. What is nanomedicine? We define nanomedicine as a way to preserve and improve human health using nanotechnology, using molecular tools and molecular knowledge of the human body. Now, in this sense, nanomedicine can be conceived as a single cell medicine, a medicine capable of curing a single cell. And so it pairs up with the fantastic applications we can have from nanoparticles once we engineer their surface. For instance, here you see uses that we already mentioned before, through which a surface that have been treated by a coating of nanoparticles becomes totally cannot be affected by water. And the same in displays, where the surface is free from adhesion of, for instance, dirt or fingerprints. Now, to achieve a nano device that will be able to be used for therapeutic or diagnostic aims, we can conceive a following scheme. We can prepare a nanovector with a certain degree of complexity. Here I've introduced oligonucleotides, for instance, as a drug. I've put a chromophore that allows me to monitor where the vector in the body is going. I put a contrast agent that allows me to increase the monitoring by imaging, enhancing the contrast of the image. And finally, I put an antibody to achieve the targeting towards a specific organ. So nanotubes in general now appear, or nanomaterials, I using nanotubes as an epitome for any nanoparticle, appears to have physicochemical properties that we can assess in the lab when we create it or modify it. But then it is further modified by the pharmaceutical intervention. For instance, pharmacologists can put a drug on it, and then it is studied both from a biological point of view, in vitro or in vivo, as well as in clinical tests by a medical doctor. In general, nanomaterials can be very complex objects because they can be made and engineered to carry on their surface proteins, DNA, fluorescent tags. So possibilities become infinitely many when you consider that you can add organic as well as inorganic functional groups on the surface of the nanoparticle. And here you have a final scheme of a multifunctional nanoparticle. On this particle, I've imagined to put two types of drugs, red and blue, a contrast enhancer. What is a contrast enhancer? We have already hinted before, namely some molecule that will allow me to enhance the contrast of imaging device, a permeation enhancer that allows me to enter more easily into cells, as well as remain for a longer time in the hematic torrent, in the hematic stream, so that we can have the particle running in the blood circulation for a long time, so that with this stabilizing element, the probability that the drug will be delivered where it needs to be delivered will be enhanced. We can have also targeting moieties or polyethylene glycol as a biological surface modifier, so that we can really end up dock into some specific receptor that will constitute an interest for us. For instance, we want to target the liver, we want to target the brain, we want to target another organ in the human body, we can do that. Show you here in the early days what we were able to do. These are images from 2003, research published in 2004 by our group, where we started from multi-walled carbon nanotubes, treated them by strong oxidating agents. In particular, here we boiled them in nitric acid, obtained shorter and straighter nanotubes. These are multi-walled nanotubes. We can tailor the morphological characteristics of the nanotubes by adjusting the solution of the nitric acid. And then we grew a nanoparticle of silicon dioxide, silica, as it is normally called, by taking advantage of the defects that we created in the nanoparticle, on the nanomaterial, by the oxidation. The oxidation will put a lot of carbon COH groups, carboxylic groups, on the surface of the multi-walled nanotube, and we will use these groups as a docking, as an attachment for new, very complex molecule. It's obtained by a precursor in a complicated but standard technique of growing nanoparticles in a micelle. Micelle is actually reverse, is obtained not in oil in water, but in water in oil, micro emulsion. And inside these micelles, we can grow with a predefined size nanoparticle of silicon attached bonds chemically to the carbon nanotube site where the defects are. And here you see the real examples of the devices we created with the nanoparticles that are placed in different defective sites of the carbon nanotube. We can engineer these devices for applications. Now, we need to immediately worry what is the biocompatibility of this device. And here you see a complete study that was carried out by our group already in 2004 to assess the cytotoxicity of this type of devices. Here we study proliferation, how the proliferation is changed. But in particular, in this slide, I show you the apoptosis. So that is the programmed death of cells induced by the presence of different doses of these carbon nanotubes modified appropriately. And you see different signals of the apoptosis. For instance, in panel B, you see pycnotic nuclear DNA condensation, blue or purple, and membrane blabbing, two typical features of a cell that is undergoing apoptosis. So now we stop and take up more questions.
Stefano, yes, we have many. And the one I would like to submit you is really related to biology. So Rita asked if can we ultimately use nanoparticle to change the cell itself completely, for example, to turn a prokaryotic into an eukaryotic?
I don't know. It's an interesting question. I never thought of it. I'm not aware of anybody doing that. And at the moment, I cannot imagine what would be the strategy to do it. But I will keep this in mind. And if you write me, I will try to give you a more concrete answer. I'm not prepared to answer this question.
And another question concerns the fact that since this nanoparticle enter our body, can happen that the body recognize this as something harmful and attack the nanoparticle. Can we avoid this?
Good question. Here you see in this slide, I'm using, probably I didn't mention, but it's written in the slide in A, panel A. You see that immunofluorescence images of Jurkat cells. What are Jurkat cells? Jurkat cells are T cells, part of our immunitary system, and we back in 2004 believed that these cells would be the most interesting to study when they face the entry of a nanoparticle in the body. It turned out after several years of study that in fact these cells are not the most involved ones. Phagocytes are mostly involved with treating nanoparticles and clearing nanoparticles from our body. So the question is, that is why I need, if I want to use nanoparticles for drug delivery, I need to preserve them in the hematic, in the circulation, in the blood circulation. I need to keep them artificially. Otherwise, our immunitary system will get rid of them right away. So the question is very well posed, and the answer is that we engineer the nanoparticles according to their use, taking into account the interaction with the immunitary system.
Another question concerns more a physics behavior of this object, and the people is asking if we have account for quantum effect while working with nanotechnologies.
Very nice question. Nowadays, this is one of the topics where the interest of different governments is being put. The two areas of application of quantum technology are mainly space and defense. Quantum technology, nanotechnology can help a lot in quantum technology. In fact, I must say that the European Union has put now 1 billion euros to finance this type of researches in what is called a flagship program, similar to what was done before with graphene. My group was part of this graphene flagship starting in 2014. More recently, this quantum technology flagship is assessing how quantum features can help technology. And from the nanoparticle point of view, for instance, quantum dots are, which I mentioned at the beginning of, in the first part of my talk, they are certainly quantum behaving features. Any device that is based on, for instance, superconducting materials with nanostructures will display interesting features from the quantum point of view. It's a science that needs to be further developed, and the technological applications are just at the beginning. This is one of the most fertile areas. And if you have more specific questions privately, I will be happy to address to relevant literature.
There are also questions concerning morality, let me say, ethical problems, and which is your opinion in this respect?
Well, I mean, my opinion is very pragmatic. I mean, a hammer is a hammer. You can use it to put a nail in a useful device that will give a shelter to a homeless person, or you can use it to hammer a person in the head. These are tools. It depends how we use them.
Thank you, Stefano. I think we can go ahead. Please tell us something more.
Okay, thanks. Now the road becomes more plain. We are going to talk about successful uses and safe uses of nanotechnology in health and the environment. So I'm now specifically focusing on medical applications. So biocement is the first application I want to consider. First of all, considering bone applications and then tooth application. So it's been in use now, biocement, for curing different diseases. Here I show you how an infiltration of biocement can fix up microfractures at the level of vertebra. It can be also done at the level of skull. And here you see dental applications. They're commercial. This is a toothpaste sold in Italy, which fixes problems in different parts of the tooth by introducing nanoparticles as a repair in them. Let's get into more advanced topics like cancer therapy. Targeted nanodrugs have been used for now decades to cure or to help the therapy in oncological applicative areas. Here I reviewed with my collaborators the state of art about 6 years ago. Now, let me give you an example, very old example, 2003. Iron oxide nanoparticles. So this is a magnetic application. It can be done by other physical methods. It's essentially hyperthermia. Hyperthermia is a therapy for cancer that is in use since the 1950s, very old. However, it basically boils down to frying the tumor. You put a needle in the tumor tissue and put a temperature and heat it up to what? Up to 45, 46 Celsius. That is the temperature where cells are breaking up. They are wrecked. And so the problem is that you essentially ruin the whole tissue, not only the tumoral cells. Here, nanotech can come to the rescue to help to make this therapy specific. So rather than frying the whole tissue, it's going to heat up only the tumor cells. How do we achieve that? There are many ways. Other ways I didn't mention, I'm not going to mention here, just briefly, have to do with radio frequency and gold nanoparticles. But here, it's magnetic nanoparticles, actually super paramagnetic nanoparticles. Concretely, these are oxides, iron oxides, Fe2O3 in gamma phase. It's a particle that when you apply a magnetic field, gets a magnetization. Switch off the magnetic field, the magnetization vanishes, disappears. Change the direction of the magnetic field, you change the direction of the magnetization. So easily, by introducing a magnetic field that oscillates, you can obtain an oscillating particle. This oscillating particle means, in an ensemble of particles, means increasing the temperature of the group of particles. Now, it's very easy to send the magnetic particles only to the sick cells, only to the affected cells, by coating them with sugar. Sugar is, of course, energy, and tumor cells are fastly replicating, so they need to suck up, to ingest a lot of sugar. So they do that. Then by oscillating the magnetic field, we can increase the temperature, as is recorded in this graph, up to 46 Celsius. Here you see preclinical tests of glioblastoma. Glioblastoma is the most deadly form of brain tumor. Here you see the tissue of a rat, the tumor tissue of a rat, where glioblastoma has been introduced, and the nanoparticles are essentially present in all the tumoral tissue. And then the treatment is quite successful in the sense that it has been even tested on patients, 15 patients. It makes the life of the rats, if I remember correctly, 4 times as long as the rats with no treatment. Here you see a thermotherapy of the targeted areas in the eye of a rat, and the temperature reaches 49 Celsius. Of course, it's very interesting to use this type of therapy, at least to weaken the tumor and then use chemotherapy or radiotherapy, but also to reach tumors that cannot be achieved, cannot be reached by surgical treatment. In this sense, the magnetic properties allow us to marry therapy and diagnostics. It's well known since decades that we use magnetic fields for diagnostics. This is called magnetic resonance imaging. It is based on the injection of magnetic particles, for instance, magnetite. In this experiment, magnetosomes have been used. This is a particular type of drug delivery particles. Here, they used to carry magnetic particles on them. At the same time, as you observe the tumor in vivo, here you see a mice, at the same time, with the same magnetic coil, you can achieve the oscillation of the magnetosomes, and so induce by hyperthermia the disappearance of the tumor after 30 days of treatment. Here are the details, which we don't need to get into now, but the point is that you can deplete and document the depletion of the tumor at the same time. So that's why we call it theranostics, therapeutic and diagnostics. That introduces the notion of diagnostics. Diagnostics normally is made by large laboratories. Laboratories that work with different analyses carried out manually. What we want to do is put this entire diagnostics on a simple chip. This is exemplified here. You see a chip that is smaller than your credit card, where the on-chip lab is able to provide an instant analysis by fusing and sorting, for instance, here 2 trains of droplets. There is a microfluidic device with a railroad-like channel and a guiding track. Now, Sensors can be a very wide class of devices for diagnostics. Here you see sensors based on spectroscopy. It's a physical characterization technique invented by an Indian physicist, Raman. That is why it's called Raman spectroscopy. It's a vibrational spectroscopy that tells us something about the vibration of molecules, and is able, when is conjugated, paired with nanotechnologically engineered substrate, to give us information about very small quantities of analytes, of substances. This is called surface-enhanced Raman spectroscopy. It is to be used when the signal coming from few molecules cannot be observed. It's too small. So by putting these molecules on an engineered nanoparticle substrate, you can obtain a distribution of what they're called hot spots. On these hot spots, typically in the position of the nanoparticles on the substrate, the molecules that are being deposited on these hotspots give us a signal that can be 1,000,000 times higher than the normal signal that would give on a standard surface without nanostructure. So that gives us the possibility of targeting and detecting substances, from dangerous substances to tumor cells, and thus provide applications that range from anti-terrorism to the hospital, to the clinical applications. This is exemplified here. We need to have biosensors also for homeland security, anti-terroristic. Here you see the surveillance area. Then you see a control center, which is networked. And then you find here on the right-hand side, the protection services that monitor the whole process. But the whole process is based on the use of a sensor. In the yellow box on the bottom, on the right side, you see the analyte detection device that will be connected by this complicated network in order to survey, for instance, the appearance of a virus in an area. Biosensors based on DNA chips are also in use. In fact, this is part of a project that I directed, financed by the NATO organization between 2011 and 2017. You can monitor by, you can analyze different samples, human samples like blood, urine, or saliva, food samples if you want to analyze sophistication or alteration in foods, to environmental sample if you want to monitor the state of waters and pollution in water, soil, or air, or vegetation. The intermediate step is to introduce bioreceptor, typically enzymes or antibodies or nucleic acids, like we did in our project. And then you need to introduce a transducer. So that's electrical interface. That can be a nanoparticle, a nanoelectrode, can be a nanowire array. And then finally, you need the electronics of acquisition with an amplifier and a processor of the signal. Here's what we achieved by electrochemical sensors in our project. We use composite materials where we inserted carbon nanotubes modified by aminic engineering molecules, and graphene nanoparticles. And the performance, as indicated by the peaks in the graph, is not good for carbon nanotubes and is instead excellent for carbon nanotubes modified as well as for graphene, because you see clearly peak-shaped curves. That explains, that testifies the performance of the sensor. More recently, we use a different type of application of nanotechnology based on optical properties. This is a project that I'm leading since 2018 and will last until 2021, where we see different types of polymers used as a matrix, where nanoparticles are arranged in a periodic structure using holograms, using two lasers that create a holographic distribution in a grading or a lattice of these nanoparticles. That gives endows the crystal, these are photonic crystals, with specific optical properties, for instance, a refraction index, which we can measure with extreme precision up to the 4th digit. Then the deposition of very tiny quantities of analytes, for instance, biological toxins or chemicals or viruses. How small? Well, less than 100 femtograms, okay? So we're talking about 10 to the minus 13 grams, can be detected by either the variation of the refraction index or the Raman, surface-enhanced Raman spectroscopy, which I mentioned before. So now I'm ready to take up further questions before tackling up the next part.
I have to unmute my microphone. There are questions concerning how you can target a tumor using nanoparticles. So how can you really send the nanoparticle on the cancer cells?
Okay, sorry, I'm fixing my screen because something happened to it. Just a minute. How can I target? Yes, okay, in the case of tumor, typically we inject the nanoparticles inside the tumor, for instance, by transperitoneal injection, if you want to reach the prostatic cancer, for instance. So now, in Germany, this therapy is in use since a decade in the hospital in Berlin called La Charité. And other ways, of course, we can inject in the blood and then put some moieties to target an antibody, conjugated antibody.
Another interesting questions concern the possibility to reuse nanoparticles. So the question said, the nanoparticles are used only once, or they can be used many times, reused, let me say.
Yeah, well, typically they're used only once. And in fact, one of the problems we need to deal with is how to dispose of the waste. So pretty much like we do when we change the oil in our car, we need to dispose this waste in a special, treating them as special waste. So, but the nanoparticles, in principle, there's no point in reusing them. We can manufacture more. I don't think it makes too much sense. But of course, one can think when you have a device made of nanoparticles. Maybe I will not have time, but one thing we do is producing filters for water remediation made of graphene platelets. Then, because the material is costly and because the material is difficult to treat for waste, in this case, we regenerate the filter by different methods. For instance, inverse pumping, or electrical fields. So, but it's a good question. It depends. I wouldn't talk so much at the level of particles, but recycling the devices made of particles.
I'm sorry, but we are running out of time. So, Stefano, please conclude your presentation.
Thank you very much. Now we are going to tackle the issue of nanovectors for drug delivery. So this. Let me introduce first the therapy based on the controlled and targeted delivery of drug. Basically, I want to illustrate why this is interesting. We have problems with all drugs nowadays in our society because we need to achieve a desired range of concentration of the drug in the body in order to obtain the desired effect. This is exemplified by this blue band or pale blue band in the graph. Now you see that the minimum level and the maximum level are well defined. And in my model, I inject a drug or I give a pill in a dose that is amply sufficient to be in the desired range. In fact, normally the drugs are given to a level that is a little bit higher than the maximum desired level. So that explains why we have side effects. Side effects are due to the fact that for a certain time, the level of drug is too high. But that's because this concentration of drug is going fast down. And so we need to give a second dose. You are familiar when you take paracetamol for your fever. After 12 hours, you need to take another dose. Now, if you use drug delivery using nanoparticles, the situation is completely different because one single dose can be enough for a very long time to give a concentration of the drug that will stay below the maximum level, thus killing completely undesired side effects, and at the same time making it minimal the need to repeat the dose. What do we use as a vector? Well, we can use liposomes, we can use nanocapsules, we can use dendrimers, depending on the specific drug and depending on the specific disease. Here I show you an example, nose to brain delivery. There is a problem. When a drug is swallowed, we have a blood barrier. This is called a blood-brain barrier that does not allow the drug to reach the brain. So that explains a lot of the difficulties that now we have to treat, for instance, Parkinson, Alzheimer, but also antidepressant or dopamine is not reaching very efficiently the system. So what if the drug is now for curing a neurological disease? It's not a drug for curing, I don't know, headache, but curing specific neurological disease. Well, you can have three situations. The drug crosses happily the membrane, very rarely, and reaches the brain. Or it takes care of the pathology only indirectly because it cannot cross the blood barrier, and so the blood-brain barrier. And so you're not using the proper drug, and you have a lot of collateral effect because you need to give a lot of the drug. Or you have an invasive care. You inject lumbar injection or surgical treatment. Now, an alternative is to take advantage of the axonic terminations of the olfactory bulb. You use two transport routes through the nose, the axonal transport and the transport between support cells. Here is a graphical representation of the axonally mediated transport on the right-hand side. You see in the step one on the left of the image on the right-hand side, dendrites absorb the drug. Then the axons allow the drug to be transported and then streamed into the brain. This can be delivered by a very simple device like aerosol that allows to deliver it to the olfactory nerve, olfactory bulb, and then to the brain by self-administration. To do that, however, we need to solve the problem of clearance. There is something in the nose that is called mucociliar clearance. The cells of the nose are equipped by cilia. The cilia move in a synchronous way to eliminate everything, powder, pollen, viruses, to eliminate the drug and send also the drug, unfortunately, and send it to the rhinopharynx and then to the stomach and elimination. That's why we decided to use muco-adhesive nanovectors, the solution we practiced last year, encapsulating a drug. We use dopamine, and that allows to increase the retention time in the nasal cavity. So that allows the drug to reach the target. This is an example of drug delivery we successfully achieved with the financing of the Italian Ministry for Health, 2011-2014, collaboration with the Rome Pediatric Hospital called Bambino Gesù. And we delivered essentially micronucleic acids, microRNA, using carbon nanotubes. Here you see the vector we prepared is carbon nanotubes conjugated with a polymer, with an aminic polymer. Both ingredients are toxic, but when they are conjugated suitably, engineered, the toxicity dramatically drops down. They are loaded with microRNA and then delivered. Here you see the in vitro analysis, an example in transmission electron microscope of the internalization, the famous biocorona I showed you in the second part of my talk. You see the vacuola that has been created inside the cytoplasm of this UVEC cell. This is a UVEC cell, cell model. And in the vacuola, you can see very magnified images with the bar is 200 nanometers of very short carbon nanotubes and aminic polymer loaded with the drug. In vivo, what we did was to put this therapy onto several mice, and we documented the increase by more than a factor 2 in the lowering of the symptoms. Essentially, this disease, which is a disease affecting the epithelial lungs of children, this is why it's called pulmonary hypertension, pediatric pulmonary hypertension. Essentially, is a deadly disease. In 9 months, children normally die. This therapy allows the number of blood vessels and the length of the blood vessels to be kept under control. And that gives interesting perspectives in general in all the diseases that have to do with vascular degeneration. So vascular remodeling and therapeutic angiogenesis can be achieved. In few minutes, I want to treat the graphene, which would deserve
Stefano,
by itself.
I'm sorry to interrupt you, but we are really running out of time.
Thank you very much.
And so I think that I will pose you just a question that is, since you said that the nanomaterials enter the cell, is there any risk that they remain there and cause, for instance, some damage? So how can we are sure that these materials are then ejected by the body?
Now, they are ejected. The cells, it's documented that the cells normally uses its own standard means to implement exocytosis. However, the real challenge now where people are working is the, the so-called digestion of the nanoparticles. We can use, in fact, there are experiments simulating what happens through the leukocytes. It's the leukocytes in our body that are doing the job. And the same action can be simulated in the laboratory using mieloperoxidase of human origin to degrade carbon nanotubes, graphene, any type of nanoparticle. And it's very successful. The biodegradation produces catabolites that can then be kept under control, at least in the lab and in tests in vitro so far, in preclinical tests. So I'm very optimistic about this, that we can achieve a complete cycle of endocytosis, exocytosis after the release of the interesting load carried by the nanovector, namely the drug.
Thank you, Stefano. I remind all the attenders that they can contact directly Stefano if they have questions.
You see my email in this slide. That's why I put it on.
So thank you again, Stefano, for the very interesting talk you give us today. And to everybody, I said we will reconvene in another room for another talk about, again, nanotechnology. See you later.